Hello, in this video we'll be talking about motion graphs. Motion graph happens to be nothing but the continuation of the previous topic that we talked about. It's a part of study of kinematics itself, study of motion. Okay, there are three different types of motion graphs we will be studying. Let me just make a chart of them. Okay, the first one would be the distance time graph, and the other one would be speed or appropriately it would be velocity time graph. So let me just abbreviate them as DD graph. That's the short form. It would be called as VD graph because it's always like velocity time graph, and the next one is acceleration time graph. So that's a long name, acceleration time graph, which happens to be AD graph. Okay. In order of importance, I would say that speed time graph comes first because there are a lot of things that I can figure out from the speed time graph. Okay, if I have a speed time graph, I can find out the distance that an object travels in a given time, which happens to be which can also help me calculating the displacement as well. Okay, that's my displacement. Let me just make it short. Another thing is I can calculate the velocity or the speed of my object at a given time, and also I can calculate the acceleration of the object uh, at any given time. So speed time graph helps me in calculating or measuring whatever. Three different important aspects of a motion of an object. So distance, velocity, and acceleration gives me an overall view of the motion of an object. That's why it's called as an important motion graph. As I told you, in order of importance, speed time graph or the velocity time graph comes first. Okay, the second one would be the distance time graph, where we can calculate, of course, the distance. We can actually read it from the graph itself, distance, or in other terms, displacement. Okay, and the second thing that we can study from this is the velocity or the speed. Okay, so distance and displacement and velocity can be read off from the speed time graph, and well, that's the third one there. Okay, and I would say that acceleration time. Okay, one important thing is that this is like kind of beyond the scope of this video, but still I'll tell you that using acceleration time graph we can calculate the acceleration for body. Well, because that's the property, that's a name, right? We gave it to the graph, so that's like we have a graph where acceleration is plotted on with respect to the time. Okay, and the next thing that we can study or we can actually read out from the acceleration time graph is the velocity. So yes, we'll be like devoting very less time probably on acceleration time graph. So so this is how the flow of the video would be. First of all, we'll be dealing with a distant time graph. The next we'll be dealing with speed time graph, and acceleration time graph as well will be kind of discussed a little bit. Okay, so let's start with the distance time graph. That's distance time graph. I have three different types of distance time graph. We got, okay, let me just make it like a chart form. We have a body which I was going to be calling it a stationary body. Stationary body, which is in our terms can be called as not moving. So a body which is not moving is called a stationary body, or a body which is sort of not moving at all. Okay, so let me just draw a graph where on x-axis I'm always going to plot the time, and there is my y-axis. So on x-axis I told you we're going to be plotting time, and on y-axis I will be plotting that's distance. Okay, that's distance traveled. But if you see the body is not moving at all, so at every time we're going to figure out that if a body is at some particular distance, say let me just say call it as 5, it will remain so at any point of time, we call it. Okay, so the DD graph for a stationary body will look something like a straight line, and that happens to be parallel to my time axis. So a stationary body in a graph looks something like this: a straight line parallel to the x-axis. Okay, that's what about the stationary bodies. Let's talk about a DD graph for a body which is like moving with constant velocity, a body which travels the same distance in the same given time. So that's my DD graph. That's my DD graph there. DD graph for a body which is moving with a constant velocity. That's y-axis, and that's my x-axis. X-axis, and I'm plotting time over there, and on y-axis I'll be plotting t. That's distance again. Okay, as I told you, every equal interval of time, the distance will be moved, equally. That means equal amount of distance will be moved by body. So, well, if suppose I call this is 1, 2, and 3, and that's time 1, 2, 3, 4 seconds. And if I want to plot the graph, it looks like, okay, at the end of the first second it travels a distance of 1 meter. At the end of the second I would say like it travels a distance of 2 meters. And at the end of the third second it looks like, okay, it will gonna be traveling 3 meters. Okay, and if I join all those points, it looks like it comes out to be a straight line. But this time, I mean, unlike the DT graph of a stationary body, this straight line would be making some angle with my time axis. So over here, this is the graph for a body which is moving with a uniform speed. It's uniform speed, or I would say like constant velocity. Right there. It's constant velocity. That's a DD graph with a straight line and making an angle with the time axis. Now I'll be talking about DD graph for an accelerated body, which probably we won't be gonna will be not using a lot. Instead, like only there is one situation where we can actually be studying the the distance time graph in freely falling body. Okay, let's come back to the topic here. DD graph for an accelerated body. Now, what exactly acceleration is? Acceleration is the rate of change of rate of increase. I would say, like, because it's an acceleration. So, in general term, acceleration or deceleration is nothing but the rate of change, right? So, when I say acceleration, it's rate of increase in the velocity per unit time. So, let me just draw it this way. Same thing that I'm drawing over and over again. That's my time axis. That's my y-axis being plotted, and I'll be plotting d there. That's the distance. When the body is accelerating, speed will increase, speed of the body. And if I say that the speed of the body increases, that means every time the distance that it travels will also increase, right? I mean, it will going to travel a larger distance as compared to in this particular second as compared to the previous second, because the speed has increased to a little bit value. Let me just put some points here. Let's see if it makes sense. If I say that, okay, the body has traveled for say 1 meter in 1 second, possibly. Okay, let me just put it this way. It's 1 meter in the first second. In the second it would probably be moving by say 1.5. So that makes it like around 3 meters. Let me just put the numbers as well. We're gonna make it more clear. Yeah. So at the end of 1 second, it was 1 meter traveled. At the end of second it traveled for now. I would say like 2 meters. So it has totally traveled 3 meters in 2 seconds. In the third second, he will be traveling more than 2 meters, so possibly somewhere beyond this particular point. And if you analyze and if the graph were having proper, you will realize that the graph comes out to be a curved line like this. Okay, so it's like curved upwards. It's more like kind of parabola, we call it. So it's the shape that will be like looking here is called as parabola. It's more like kind of curved upwards, more like this. Okay. All right. So that's the accelerated motion, where you will figure out that the 3D graph moves upwards or curved upwards. Okay. So what about something called as deceleration? If there's something called as deceleration as well, where a body decreases speed. I would say, like, where the rate of change of, or I would say, like, rate of decrease of velocity kind of, like, decreases, I would say. So let me just call it this way. I got another graph where the body starts with higher velocity and eventually decreases and, well, becomes flat because starts from higher velocity and decreases to zero. When the velocity of the body decreases to zero, it becomes stationary. That means it would be parallel to my time axis. It's more like, the first dd graph that we talked about. Okay, so that's the dd graph that we have. Okay, now before I can start with the VD graph, I need to give you a few examples of DD graph and how to analyze the DD graph thing. Okay, so let's have a few examples of DD graphs. Okay, let me just give an example. Let's see if I can paste one. Oh, there it is. Alright, so that's one of my examples that I want to give you. I should have actually cleared the background, but anyways, that can help in a little bit. Okay, so as you can see here, that's the distance that is traveled. That's the time that it takes, like, required by a body to travel. Okay, if you look closely, there are three different parts of this particular graph. There are three different parts in this graph. That's one part. Okay, that's one part from 0 to 4 minutes, I would say. And there is another part where it's kind of a flatter line, and from 6 and up to 16 it seems to be a line which which rises up. So if you remember the DD graph that we discussed, if you have made proper notes of them, you realize that from 0 to 4, since it's a straight line and making some sort of angle with the time axis, this is a point where, let me just write down, this is 1, and 1 would be where there is uniform speed. That's the first stage of the journey. Second stage is, since it's a flat and it's like parallel to the time axis, this would be stationary because, well, as I told you, for a stationary body, the graph would be parallel to the x-axis. And again, you will realize that the graph, like, kind of moves up. It is a straight line though, but it's inclined to the x-axis with some angle. Well, that's uniform speed again. So there will be a question like, what's the difference between 1 and 3? When you say that it moves in with a uniform speed in stage 1 and stage 3, what's the difference between them? Okay, as I told you, it's inclined. Now look at this. It's a very important part. Is how do I calculate the speed from a distance time graph, because that's an important stuff, and in order to do that I need to just make more space. So just wait. Alright. Okay, I got it cleared, and I displaced this thing on one side. So let me just get started. I would say, like, for a journey where, for a part where it is like between 1 and 0 and 4, from 0 to 4 seconds, I would say that alright, the change in the speed, the distance, I would say the distance that it travels is 1 kilometer. So distance that it travels is 1 kilometer, and the time that it takes is 4 minutes. So let me just write in the simplest thing possible. So my velocity will be distance upon time, this 1 over 4, and that happens to be 0.25 kilometer per minute. Well, that's so small there, I just have to cram it up. Okay, so this is the speed. The number that you are looking at over here, the 0.25 kilometer per minute, is it's the speed of the object during this period from 0 to 4. Now when I say that, okay, it reaches it reaches 1 kilometer, and somehow it remains stationary for around 2 minutes before he starts moving again. So that's like velocity in the second part would be stationary. Let me just write from no, it should be 4. So from 4 to 6, the body is stationary. So the velocity would be obviously 0. Okay, now the next part starts. We got this where the velocity starts increasing from 1 and it goes on increasing till 8. Oh wait, not the velocity, but the distance. It starts moving from 1 kilometer and it moves on and goes up to 8 kilometers, right? So it travels 7 kilometers in so many minutes. So how much is that? 16 minus 6, that gives me 10, right? So let me just write down for 6 to 16 minutes was happening from 6 to 16 minutes. It's minutes, right? So let me just make it more clear. Actually rectify it. That should be minute there. My bad. Alright, 6 to 16 minutes. I'll again say that, okay, the distance that it travels is 7 kilometers. The time that it takes is from 6 to 16. That makes it, 10 minutes possibly. So if I calculate velocity, it should be 7 over 10, which happens to be 0.7 kilometer per minute. Okay, so now you got another number here, which is 0.7. There is a relation between how much inclined the line is from the x-axis and its value. Now look at this. We can also calculate. The thing that I'm doing over here is something called as, in mathematics we call it as gradient. So, important thing to note down. In distance time graph, the gradient of the line will give you the velocity or the speed. So logically, if suppose I have some sort of dt graph over here and I need to find out, say, the speed between 0 to 4, I will calculate the gradient of that line. Gradient of that line is the rise over the run. So that's rise is of 1 kilometer and run is of 4 minutes. So that's 1 rise over run. That's 1 over 4 kilometers per minute. So that's 0.24 kilometers per minute. Okay. Likewise, if I need to calculate the gradient over here, I mean it should be like rise, and rise happens to be from this value and all the way up to 8. So my rise is from 1 to 8, and that is 7. The run is from 6 to 16, so that's 10. So the velocity is 7 over 10. So again, I am actually calculating the gradient. If someone asks you, what is, okay, tell me what is the speed over here at this some particular point, let's say 12 point, 10.4 seconds. What is the value of velocity? Well, since it's a straight line, it's a straight line from here up to here, a straight line, we're going to have a common gradient every time. Okay, suppose I'm talking about this particular line. So if this is a straight line all the way from here to here, it will have a common gradient. So well, at every point on this particular line, the speed or the velocity of the object would be 0.7 kilometer per minute. So important thing is that we can calculate the velocity from the distance time graph by calculating the gradient of the line. So a gradient of a dt graph gives you the velocity. A very, very important stuff to remember. Okay, so that was one example, and I would like to give you another one. Here it is. Okay, that's some animal fellow who's like kind of running from one place to another. Like it starts a journey from here, from this end. Okay, and it goes up to some point A, and it seems like it from A to B and B to C. Now if someone asks you, okay, describe this graph, I mean, how can you, what idea of motion you get from this particular graph? So if you analyze this graph with the information that I already gave you before, it seems like, since from 0, I mean, let me just call this point O, because that's the starting point, right? So let me just call this as point O. Point O, this is point A, point B, point C, O, A, B, C. Alright, from O to A, it seems like the line is like kind of a straight line, and it makes an angle with the x-axis. So from O to A, it's uniform speed. Uniform because, well, it seems like it's a straight line. Okay. We'll be calculating what the uniform speed is there. Okay, we'll be calculating the speed as well. From A to B, it's again, you see, like, it's kind of it's like a straight line, and which is flatter, I would say, like it's parallel to the time axis. So I can call this to be body to be stationary in this part. So of course that will be not a problem for me, because yes, during A to B the body remains stationary. Okay, and again it seems like it again starts moving. Well, there is a glitch here. I mean, what exactly, it is like going down or something? Yeah, of course, B to C. It seems to be like it starts from home. That's my home up there at the 0 level. Okay, I ran for around 1 kilometer. I kind of rested for a while there. Okay, and I turned back to home. So yeah, of course, it's like kind of my return journey. Like O to A is like from my home to some garden or something, and I rested there for a while, and then I came back over here. And B to C is like like coming return journey from garden to the home. So right, that's so sort of moving between B to C. All right. So let's see. I would write that from B to C, it's moving again, uniform speed. Alright. If you find out the gradient of this line, I would say gradient is equal to the rise, which is from 0 to 1, that's my 1, divided by the run, that is from that's a nice line actually, it's a color there. Okay, I need to just think about this particular line because that happens to be quite let me just check. Alright, sometimes it's very difficult for you to analyze what that line is. Okay, so it's important, before you jump onto the formula and plug in the values and calculate the wrong value, be sure about what you read off. So it seems like this has to be 6, then 7, 8, 9, and then 10. So yeah, that's 6. So well, that's my 6 up there, and 1 over 6 is okay, it's 0.167. Well, that seems so, and the gradient is nothing but the velocity, so the unit would be kilometer per minute. So let me just write kilometer per minute. Velocity, of course, here would be 0 because it's flatter, and over here again my rise is 1 divided by, let me just see how much is the time, 2, 3, 4, and then 5 again, and that's 1 over 5, which happens to be, I think, 2 or something. That's what it is, and that's kilometer per minute. So that's what it is. And if you find out the gradient comes out to be negative for this, so let me just put down, okay, when I talk about the uniform speed, I will not be putting the negative sign there. That's the basic difference between the speed and the velocity. Uniform speed is just 0.2 kilometer per minute, but when I say that, okay, what's the velocity, you need to say that it's negative 0.2 kilometer per minute. Well, because it's the return journey. Okay, so that's all about the DT graph we'll be talking about. We're gonna see in the next video how to analyze the VD graphs with few more examples. Okay,